Pre-calculus students, today we're going to take a look at a new topic, parametric equations. It'll connect back to some things we learned a while ago with our conic sections, so hopefully you'll have some recollection of that. But let's get started. Let's talk about parametrics. Well, what are they? First of all, maybe I should start with this scenario. If we were to graph something like the path of a golf ball, there'd be different ways to think about it. One way, the first graph over here, is where this represents time, that's the x-axis, and then the y-axis represents the height of the golf ball. So you get this parabolic shape. It's gravity taking effect, right? And so we get that shape. But one thing that graph doesn't consider at all is horizontal distance. It may look like we're saying that's the flight of the golf ball or the path of the golf ball, but no, this is time. This isn't horizontal distance. Over here, we have a different graph that only considers the horizontal distance with time. So here is time on our x-axis, here's distance, and that's essentially how far the ball is traveling. But again, both these graphs are limited, and to get real information, to know like where the ball's height and horizontal distance are at a certain time, we'd have to kind of do two separate calculations and piece two graphs together. So parametrics are essentially a way to get three pieces of information onto one two-dimensional graph. So here's the same graph, and I know this graph here looks fairly similar to the one over here on the left. It is the same general shape, but this graph here shows not only the height, but it shows the distance, and although you can't see it here, when we use our calculators, we can trace and find both its horizontal and vertical position with respect to time. So these are called parametrics. Again, you can see how it's entered here. We'll get into the calculator before long. So let's take a look at our first parametric. Our instructions here are to, first of all, graph it. Well, let's start there. Now, normally when we graph equations, we can create something like a t-chart, right? Well, in this case, our t-chart gets extended by one extra column because it's not just an x and a y, but it's also a time that's included in this, and that's important. All right, so normally with parametrics, we just start with time of 0. That just has to do with the idea of -1 as a time is kind of a weird concept. Don't usually have something like that apply. And then we'll go ahead and use the two equations that are given to us, the two parts of the equation. So x equals t plus 1. I'm going to be able to do this in my head. 1 plus 1, yep, that's 2. 2 plus 1, yep, got it. And now I see the pattern, and boom, done. All right, for the y values, it's always y equals t squared. Again, you can't see me, but I can promise you I'm not using a calculator, and neither should you. All right. Sorry, sarcasm. All right, so there are points. Now, realistically, when we graph, we aren't really looking at the t values when we want to sketch our graph. We're looking at x and y. So I'm going to create some little axes here that we can use, and I know that my x values go basically from 0 to 5, and I know that my 1 to 5. But then the y values go as high as 16. So I'm going to count by ones here. These would be our x values down here. And 1, 2, 3, 4, and 5. And then over here, I'm going to count by 5s, I think, because that'll get me, if I can get 4 tick marks, that gets me up to about 20. And that should be plenty good for what we're doing with this graph. All right, so let's plot our points. Again, we're not plotting t values, we're plotting x and y. So 1, 0, 2, 1, just kind of approximate these, 3 and 4, 4 and 9, and then 5 and 16. And what I think you can see here is what we have going on is a parabolic graph. We've seen these many times before. All right. Now it says to also convert into, or to graph, I should say, the rectangular equation and rewrite it as a rectangular equation. So let's start with the rewriting. Here's where I'm going to start. I'm going to take that equation x equals t plus 1, and essentially I need to solve for t, and as you know, that's a pretty simple calculation. Just subtract 1 from each side. Once I have that t value, I'm going to do y equals, and I'm going to plug in that value right there. Whoops, I plugged in t. No, it's supposed to be x minus 1. There we go. X minus 1 quantity squared. And folks, right there, that's the rectangular form. Although my handwriting could improve. That is the regular form. That's a little better now. All right, there's one other issue that we have with these. If you look at this graph, you'll notice that it's a parabola, but the left side isn't there. And it's essentially because, well, we aren't going to have negative time. So what we do to take care of that is we just set the same restriction here. This time it's an x restriction, and we'd say x is greater than or equal to 1. I'm not going to make a massive deal about those restrictions as we move forward. Anyway, it's there. So there it is. All right, and if we graph x minus 1 quantity squared, remember that's a parabola. It has a vertex at the point 1 and 0. So I'm going to mark that. There's 1, 0. And then we know the curve, it's opening up, and it's opening both left and right. But since we said x has to be greater than 1, then we know it's basically that shape right there. I'm just going to do a really rough sketch with the goal of showing you that they're essentially the same thing. All right, on our next three, our instructions are the same. We're going to use our calculators to sketch the graph, and then we'll also convert to rectangular form. Now, before you start trying to graph parametrics, we have to make sure we're in the right mode. So hit that mode button on your screen. And by the way, if you don't have your calculator out, you go ahead and hit pause right now and get your TI-84. Sorry, Desmos people, this is not the topic. Although I can show you how to graph with Desmos, you can graph parametrics, but it's a little limited on some of the evaluations, so I don't really highly recommend it for this topic. All right, so when we want to graph parametrics, not surprisingly, we need to be in parametric mode. So if you go down here where yours probably says function, go over here and switch it to parametric, and I see polar is right there too. We'll get to that eventually, but not today. All right, and then you'll notice that instead of just y equals, it's x1t equals and y1t equals, and this is what we want. And another thing you'll notice is when I type in like t minus 4, I can just hit this button right here, x, and oh, it says t. It's because when I switch modes, that's why this button doesn't just say x, it says x, t, theta, n. It's saying, depending on mode, it's essentially just the variable, whichever one it happens to be. And there we go. Now, before I graph this, though, I want to hit the window option and see what kind of values we're looking at. I actually think these the t values become really important here. I'm going to change it to 0 to 5. 0 to 6 would probably be just fine. And I want to change that step to 0.1. You don't necessarily have to do that, but if we're thinking about t values, that would help. Essentially, that's saying I'm going 0 to 5 seconds and I'm checking every 1/10 of a second. It just provides cleaner numbers for us to check with, and we'll end up right on the integer values. And I can just hit graph, and I should have a good enough window to look at. And so if you hit trace, you can kind of see what's going on. You can see where we are at 0 seconds, and if you keep going forward, you'll see I'm at 1 second here, and I went past it. But anyway, you get the idea. And that's what the graph would look like. So I'm going to drag that over here. I know you can't do that, but you can do a quick little sketch. All right, so let's convert to rectangular form. We're going to do this the same way we did the last one. We need to solve for t. So I'm going to take that first equation. I know that t is equal to x plus 4. And then I basically just plug that in the y equation. And my rectangular form would be y equals 3 times x plus 4 and minus 5. And that's going to give me the equation y equals, it'll be 3x plus 12 minus 5. And so that gives us y equals 3x plus 7. Now, one other thing we should probably mention again, just real briefly, is this graph actually doesn't extend infinitely to the left. We have a bit of a restriction there. Our least value that we would have for x would be when time is equal to 0. So that's going to be x is going to have to be at least 4. All right, again, don't be in a big panic about this restriction here, but I mean, technically that should be part of the deal if we're going to do these the right way. And you know me, I like doing things the right way. All right, why don't you go ahead and pause the video for a second and graph part B. All right, you can see my graph for b, and if you want to see what I typed in, it's not going to be too surprising. 1/2 t and t squared for the y value. And again, we do need to go ahead and do that little conversion to rectangular form. So if x is equal to 1/2 t, then t is equal to 2x, right? Multiply both sides by 2. And then I can plug that value in for t right there. So y is 2x quantity squared, which we'd probably want to go ahead and clean that up and make it 4x squared. Again, with the restriction, this time it's x greater than or equal to 0. All right, how about this? This one has a logarithm. It might scare you a bit, but I think you can handle it. So do part C on your own. All right, welcome back. On my calculator screen on the right, you can see what I punched in there for graphing purposes. No surprise, the graph looks like you see here. I'm sure you had that. The conversion on this one wasn't really too bad. A couple quick things to talk about. When we solve for t, technically we get t as plus or minus the square root of x. But essentially, we could, when we plugged it back in, we could disregard the plus or minus because you're not going to take the log of a negative number. It's impossible. So no negative here. It's just simply the log of the square root of x. Now, one other thing you may note is I put two possible answers here. If you remember our properties of exponents of logarithms, if you have x to the 1/2, the log of x to the 1/2 like we do here, you can bring that 1/2 out in front. So I'd be okay with either of those answers. Technically, the second is a little more simplified or concise, but again, it's not a huge difference. All right, on to number 3. When I read the instructions here, the first thing that sticks out to me is like, whoa, what's this? Vertices and co-vertices? What shapes could we be dealing with to have vertices and co-vertices? That's interesting. So here we go. Let's go ahead and graph this and see what it looks like. 3 times the sine of theta. And now remember, since we're in parametric mode, it's actually going to say sine of t. That's okay. It's just the variable, whatever variable it is fine as long as it's consistent. So 5 cosine of t. And I actually kind of like the standard zoom on this because it's a trig-based zoom. So you can look at it there. Now, the only thing I don't love about this, when I look at that graph right there, that looks a whole lot like a circle, doesn't it? But let's do one thing. Let's zoom square this thing. So option 5. And oh, we could have been tricked pretty easily, couldn't we? That is definitely not a circle. That is most definitely an ellipse, which sort of makes sense since we're looking for vertices and co-vertices on that level. So let's go ahead and change this to rectangular form, although I guess we could find the vertices probably first, because when I hit trace, I immediately see the co-vertices right there. They're at 0, 5, and as I work my way around, and you notice the values here are really nice. Like, look at that. You can see t is 90. So in this case, the t value is actually representing our angle. And at 90 degrees, we got 3, 0. And then if we go around a little further, as a matter of fact, I'm just going to type in 180 because I know that's going to be our next vertice. And there we go. It's at 0, -5. And then the other would be at 270. And I can see the one over to the left at -3 and 0. So we've got our vertices. Let's see. I'll go ahead and list those in the proper form here. We've got our vertex at plus or minus, well, excuse me, 0 plus or minus 5. Sorry, having technical issues here. Vertices, there we go, at 0 and plus or minus 5. And then our co-vertices, those are the vertices that are actually closer to the center, and those are at plus or minus 3 and 0 on this ellipse. All right, working on trying to write legibly too. All right, there we go. All right, so let's change this into rectangular form. Now here's what we're going to do. This conversion method is a little different than what we did on the others because it's, you know, you would have to use like inverse trig to solve for theta. That's just goofy. So here's what we know. We have this little relationship of cosine squared theta plus sine squared theta equals 1, right? So if I solve each of these for sine of theta and cosine theta. So like right here, I'd have sine of theta equals x over 3. Here I'd have cosine theta is equal to y over 5. If I do those two conversions, then I can just plug in, well, how about y over 5 instead of cosine? And we're going to have to square it because it's cosine squared. And then x over 3 for sine, and again it's squared, and that would equal 1. And we could actually simplify that just a little bit. We'd have y squared over 25 plus x squared over 9 is equal to 1. And you'll notice that that equation we found looks a whole lot like the equation of an ellipse that has a center at the origin. And although we usually do the x term then the y term, it's really the same thing. The order's not that important. But x squared over 9 plus y squared over 25 would give us an ellipse with center at the origin and all the information you see here. So hey, it matches what we've seen before. All right, now let's go ahead and graph B, and I've already punched that in. And when I hit graph, I'm going to get a look at it. You may need to pause so that you have a chance to catch up to me here, but I'm going to keep moving. So our graph on B is actually a hyperbola, which is kind of interesting. I'll leave that right there. And you can, if you hit trace, at 0, I get one of the vertices. It's 5 and 2. And if I keep tracing my way around, I'll find the other vertex. It's this point right down there, or if you were looking on the calculator, it's over here. But that point ends up being at 5, -4, and if you hit trace and go to 180, that's where it happens. It's essentially like half a trip around the unit circle. It's showing up. So there are the vertices. Now, we sort of use co-vertices to graph hyperbolas by hand, but we're not going to spend the time to find those on a problem like this. It's really not that useful to us. All right, so let's go ahead and solve for, well, actually, before we do that, I need to tell you where we're headed. Remember this Pythagorean identity, 1 plus tangent squared theta equals secant squared theta. Now, if we rewrite that, we would know that secant squared theta minus tangent squared theta equals 1. That, folks, is our form that we're going to use for hyperbolas. So if I can solve this for tangent, so I'll have tangent of t is equal to x minus 5. And then the other one, I'll solve for secant, and I'll add 1, and then divide by 3. So I'll get secant of t is equal to y plus 1 divided by 3. All right, so here we go. Secant squared theta would be y plus 1 over 3 quantity squared minus the tangent squared theta, so that's x minus 5 quantity squared, equals 1. Now, if we want to get that into the form we're used to seeing, it would look something like this: y plus 1 quantity squared over 9 minus x minus 5 quantity squared over 1 is equal to 1. A hyperbola. On number 4, we're going to go back to working with linear graphs, and then don't worry, we'll get back to conics soon thereafter. So this time we're going to look at a line segment that goes from 3, -4 to 6, 5. Now the first thing I'd want to know is I need to find the equation for this line, because it says to find the rectangular equation. Well, let's do that. So the slope would be 5 minus -4 over 6 minus 3, which would be 9/3, or 3. All right, and so we could write the equation. I'll start in point slope form. Y plus 4 is equal to 3 times x minus 3. But if we simplify that, we'd have y is equal to 3x minus 13. Okay, now that's the line that goes through those points. But if we want to restrict it to just be a segment that starts at 3, -4 and 6, 5, we could just restrict our input value and say the x value is 3 less than equal to x less than equal to 6. So there's the rectangular version. All right, let's talk about the polar or excuse me, we're not going to polar yet, but let's talk about the parametric version. When we take something like a linear equation and change it into parametric form, we always have to start with this. And I always feel this is kind of a funny way to do things, but it's just the way it works. Essentially, you just say x equals t. That's it. So you got to define x as being t, and then the nice thing about that is it makes finding the equation real simple. Just wherever it used to say x, now it says t. And again, we have this restriction of saying t starts at 3 and stops at 6. So if we were to graph that, I'm going to clear out my hyperbola here, and I could just simply type in x equals t and y equals, got to actually hit these buttons apparently, 3t minus 13. And then before I graph it, I'm going to go to the window because I want to restrict t. I don't want to go 0 to 360. That's crazy. I want to go 0 to 3. And I want my step, we can kind of make a decision on this step. I'm going to make it like about 0.1. This is basically you deciding how often do you want your calculator to do this computation. If you make this number too big, your graph can lose accuracy. If you make it too small, it can take forever and a day for the graph to actually show up. But this is essentially saying we're going 0 to 3, so this is going to have a length of 3 basically. And we're checking every 0.1, so it's going to only have to do 30 calculations, and that's very, very simple for our calculators. And I can't really see the bottom of this graph, so I'm going to hit my window and change that y minimum to make it a little smaller and see if we can't see the whole thing just a little bit easier. So I'll make the y minimum like -20. And that should show it. There it is. And I probably could even shrink that graph down a little bit from there, but I just wanted to show you what that looked like. And you can see that the graph, if you were to trace this thing, you would see that the graph does in fact start at the point 3, -4 and stop at the point 6, 5. You can do that on your calculator if you'd like. All right, let's look at the next one. It says we have a circle. All right, back to conics. That's what we like. With the center 6, -3, and a radius of 4. So I'm going to write the circular equation, x minus 6 quantity squared. Now I'm going to write this in the conic form, where instead of putting equals radius squared, we're actually dividing by the radius squared. So it's almost like I'm writing this as an ellipse instead of a circle, but it's an ellipse where both axes are the same, and therefore it's a circle. All right, so that's probably the form that, in my opinion, would be the easiest to use as you do these type of problems. So there's your circular equation in the conic form. Now, remember we said that that we have this old Pythagorean identity where cosine squared theta plus sine squared theta equals 1. So let's work the opposite way that we did before. I'm going to say cosine squared theta is x minus 6 quantity squared over 16. And if you take the square root of both sides, we get cosine theta equals x minus 6 over 4. And then if we multiply by 4 and add 6, we'd have x equals 4 cosine theta plus 6. I'm going to do the same thing with the second term. I know sine squared theta would be y plus 3 quantity squared over 16. Again, folks, these two equations are coming from knowing cosine squared plus sine squared theta equals 1, and so we're just trading. We're saying this has to be cosine squared, this has to be sine squared. You don't necessarily have to do them in the same order that I'm doing it, but to me it makes a whole lot of sense when you can to keep cosine with x and sine with y. That's something that we're used to seeing, a connection that we've made many, many times. And so then we have y equals 4 sine of theta minus 3. Or you could write it as -3 plus 4 sine theta. But there's your parametric right there. All right. One thing I would say is, like, whoops, if you're curious about that, go ahead and try graphing that thing. I don't know what I'm doing here. Sorry. Try graphing that equation. I'm trying to circle my answer, making a disaster of it instead. All right. So there's the answer. There's the parametric form. I'm going to go ahead and sketch that real quick on the calculator. 6 plus 4 cosine theta. I switched the order on that. You don't have to do that, but you have to be more careful with parentheses if you don't make the switch I just made. Make sure you close your angle off before you type in the minus 3 or the plus 6. And remember, we kind of changed the mode a little bit so that things looked a little goofy. Now this should be a circle. If I hit zoom 6, that's my standard form. Now that looks elliptical, right? But if I go back in and zoom square this thing, we'll be able to confirm that we indeed have a circle. There it is. Beautiful. Onward. All right, we're now to our last two questions today. I'm going to go ahead and stretch this screen out a little bit so I have more space. I'm not going to use the calculator on these anyway. So here we go. We have an ellipse with the given foci and co-vertices. All right, so let's do this. We have to start essentially with finding the equation for the ellipse in rectangular form. So if you're rusty on conics, you're going to have to up your game just a bit and get this figured out. But what we know from that information, we know the center for the conic would have to be at 4 and 8. That then tells me that if these are the foci, that I know the C value is 5. If you look over here, you can see that the co-vertices, that's our B value if you find it, but they're separated by 24, so the B value has to be 12. And if you remember, with an ellipse, we have that weird Pythagorean theorem thing going on where it's C squared equals A squared minus B squared. And when you have that situation, we can see pretty quickly then that A would have to be 13. 13 squared minus 12 squared is 5 squared. Now again, if you're rusty on your whole conics situation, you might have to go back and kind of refresh your memory from the first half of this chapter 9, and you can do that via your notes or just look back in the book or stop in and get some help. Make sure you get these things cleaned up. Here's another thing we know. We know if the foci are at 4, 3, and 4, 13, we know this is vertical. And I actually think we have enough information right now to go ahead and write our rectangular form. We know that the center's at 4 and 8, so we can do x minus 4 quantity squared. I'll deal with the denominator in a minute. It's an ellipse, so we're going to have plus, and then we'll have y minus 8 quantity squared. We'll deal with that denominator in a moment as well. And it's equal to 1. And we always know that the a value goes with the vertical. If it's vertical, it's the a value is going to go with the y term, is what I mean to say. So this would be a squared, or in this case 169, and over here this is the b term squared, so 144. There's your rectangular form of the conic. Now let's do some conversion. Well, we know, like right down here, this is going to be our cosine squared term. This is going to be our sine squared term, because we know cosine squared theta plus sine squared theta equals 1. And I'm going to jump ahead in the work just a little bit and say cosine theta equals x minus 4 over 12. And that would tell me then that x is equal to 4 plus 12 cosine theta. And then the other equation that we'd be dealing with, of course, is that the sine of theta is equal to y minus 8 over 13. So I'm basically just taking the square root before I write this down just to save myself a little bit of work. And then we'd have y is equal to 13 sine of theta plus 8. And again, I'm just going to flip the order on that real quick just so that it doesn't get too confusing. And there we have it. I'm going to rewrite it. I don't know that you really need to do. Actually, here's what I'll do. I'll just rewrite the y term. There we go. So 8 plus 13 cosine theta. And there is my parametric right there. Again, if you want to check these things, you know how. Just put them on the calculator and see what it shows you. All right, our last one. This time it doesn't tell us which conic it is, but it tells us that we have vertices and foci. Now, if we know the vertices are at 3, 3 and negative 5, 3, we know that the center is at negative 1, 3. We know that the a value here would have to be 4. And then let's see, we have foci that are further away from the middle than the vertices. If you just did a quick sketch of this, okay, so we have vertices at 3, 3 and negative 5, 3, but then our foci are out further this way. So we know the graph has to open up like this and this, and we know that's a hyperbola, right? So just something to keep in mind. Another thing we get from the foci information is that we know that the C value has to be 5. And remember, with the hyperbolas, we just have a squared plus b squared equals c squared. It's the normal kind of Pythagorean we're used to. So b would be 3. That means our rectangular form would be x plus 1 quantity squared. We'll deal with denominator in a second. And oh, I did do this right. I almost made a mistake. I wasn't thinking and I just got lucky. This is horizontal, so the x term has to be first. And then we'd have y minus 3 quantity squared. And we'll deal with that denominator as well. And again, we know that the a term is always first with hyperbolas. So this would have to be 4 squared. This would be 3 squared. And as we talked about before, we have this whole relationship of secant squared theta minus tangent squared theta equals 1. This will allow us to do our final step, which is the conversion to the parametric form. So I know that secant of theta is going to be x plus 1 over 4. So x is equal to 4 secant of theta minus 1. Again, if you want to switch that order, you'd be more than welcome to, and it might even be smart to do that. And we know that tangent of theta would be y minus 3 over 3. So y then, and I'll write this over here, would be 3 tangent of theta plus 3, or again 3 plus 3 tangent theta might actually be preferred, but this is fine too. All right, folks, those notes were a little lengthy, but really good stuff going on here. I hope that you're picking up on some of the patterns. You guys have a spectacular day. Come to class ready to work.